Let's continue with a new chapter. This is about direct energy deposition processes. This is somehow similar to fixed-frame fabrication and some powder-based systems, but not completely obviously similar to them. It's a kind of combination of these two approaches. I will start with an example here. This is a company called Instack, and this is how they are doing the deposition, direct energy deposition process. You see that they have a laser, and around this laser, they are also depositing powders. Once the powders are hitting the surface, with the help of this laser, they are melted and joined with the previous layer or the substrate they started the process. And the important thing is that they have such camera beside, as you see. They are monitoring the molten pole or molten pool and also the part. So if they see any unwanted things actually around, if the print is not going well, then they may fix it on the fly or they may simply stop the process. Now, in a moment, I will show you this one. Okay, this is the Instack company. It's a Korean company.
Kinetic is a world-class manufacturer of orthopedic implants for spine, knee, and hip joint, situated in Cheonan, Korea.
Yeah, this is actually showing the process. They start with the substrate. The substrate might be a simple block, box-shaped block, or it may be a spherical shape. As you see, right now they are printing with depositing powders and joining them on the spherical shape. Probably this is part of a hip joint.
Kinetic acquired the 3D metal printer by Instack 3 years ago to use in the manufacturing of hip joint implants.
여기 보시는 제품이 인공 엉덩이뼈 관절에 사용되는 비구컵입니다.
Can anyone tell me the main property of these surfaces? If you look at this part, for instance.
Roughness.
Yes, they have higher roughness. If you look at here, you can clearly see these grains. And the main thing about this process is that they have high roughness, high surface roughness values. And sometimes, for depending on the application, it might be useful, and it's useful especially with the hip joints, such implants.
외주 공정으로 지정되어 있고 이에 따라서 제조원가 상승과 납기 지연, 높은 품질의 제품을 보유할 수 없는 상황입니다. 그래서 이에 따라서 저희들이 고민하던 과정에서 메탈 3D 프린트를 제작하고 있는 전문업체인 인스택과 접촉하게 되었습니다. 기계강으로 이런 형상을 만들고 그 만든 이후에 DMT 코팅을 이용해서 코팅을 이렇게 한 상태입니다. 이 완료된 상태의 제품을 TPS 코팅을 하게 되면 이런 상태가 됩니다.
The production efficiency of this method became well known internationally.
이탈리아의 모 회사에서도
Known internationally.
You can see that there's a laser at the center, and also they are jetting some powders with the help of some channels around the laser, and they are hitting the surface, and once they hit the surface, they are melted with the help of this high power coming from the laser.
이탈리아의 모 회사에서도 저희한테 콜이 들어왔어요. 자기네들도 샘플을 보내줄 테니까 한번 프린팅 해줄 수 있겠냐고. 저희는 인공관절의 기본 구조를 다 만드는 다음에 거기다가 코팅만 하면 되는데 거기는 이 전체를 다 프린팅 해내야 되니까 비용, 시간, 저는 그 회사가 겪고 있는 고통을요 안 봐도 그냥 느낌 나요. 한국에 있는 코렌텍이라고 하는 회사랑 도저히 시장에서 이길 수가 없는 그런 구조예요. 타이타늄이라고 하는 금속을 프린팅 해내는데 어마어마한 어려움을 겪고 있어요. 실제로 성공하지 못한 데가 많고요. 쉽게 깨지고 강도도 안 받쳐지고 중간에 기포가 들어있고 이런 부분들이 있기 때문에 그렇게 하는 거죠. 그래서 그런 측면에서 보면 타이타늄에 대한 기술을 보유하고 있다는 게 굉장히 중요하다고 생각합니다.
Production efficiency is important, but good results from clinical tests are more important.
시술 후에 가장 중요한 게 초기 고정력입니다. 초기 고정력이 좋아야 환자가 일상생활로 빨리 복귀하는데 지금 현재는 수술 이후에 예후가 좋다고 지금 이제 사용하시는 교수님들로부터 연락받고 있습니다. 지금 한 300건 정도예요.
Instech has a clear goal of becoming a large-scale 3D printer manufacturer that is able to produce commercial airliner frames and nuclear power generating equipment.
선박 엔진을 만들 때 그 프로펠러 있잖아요. 그거 만들려고 하면 블레이드 같은 거 만들려고 하면 아파트 한 20층 높이의 3D 프린터가 필요하다고 하거든요. 그 배에 딱 특화되어 있는, 굉장히 특화되어 있는 하나 아니면 두 개 이 정도밖에 안 될 거란 말이죠. 그런 걸 만드는 데 있어서는 역시 라지 스케일 프린터 아니면 비용적인 측면에서거나 그다음에 그 제작 기간이라는 측면에서거나 너무 오래 걸린다는 거죠. 그러니까 거기에 걸맞게 우리가 충분히 경쟁력을 가지려면 라지 스케일로 가는 것 자체가 의미 있다고 생각하고 있습니다.
Let's go back to the slides. And I can show you an example. I had the chance to use this printer and we printed our logo of our university. You can clearly see this high surface roughness values on this shape, slightly grainy. And the thing is that you need to feel the interior of the regions. Again, as in the case of some other metal-based systems, you cannot have various infills. The interior of the parts should be completely filled. And I hacked their system. I have written a special G code and try to manufacture such an Voronoi diagram. And you can see that this, I don't know, but if you look at this cross section, each edge has a different height. Although I have written the same code for each edge, due to the actually speed of these powders, they couldn't be actually joined with the previous layer, and some parts are shorter and some are longer than the expected values. And this is mainly due to the speed of the powders, since they are jetted, and once they hit the workpiece or the previous layer, they go away and we cannot join with the previous layer. This is a problem of the direct energy deposition system, and that's why we don't prefer to print such shell-like structures. They are only preferred for covering the surface or completely covering the slices. I think there's a question. Well, okay, no question. So obviously we are fabricating the parts in this process by melting and by depositing the material in the powder form. There are also some wire versions, but we'll be mostly focusing on the powder-based versions of direct energy deposition systems. And we can do it with metal powders. There are also some ceramic powders used, but it's mostly preferred with metal manufacturing. And we are focusing our laser into a very small region. And in that region, the powders are melted and they are joined together. But the whole workpiece is not melted, and we don't have a powder vat. So these are the main differences with respect to other powder-based metal additive manufacturing system. So in summary, the powders are actually melted while they are being deposited. They are not melted on the powder beds. And for the heat source, you may use laser. This is the common way, but depending on the material, if you want to have high power, you can switch also to electron beam or maybe plasma arc. These are different types of power sources, heat sources we can use. So what do you think this process is mainly similar to? Actually, we discussed it at the beginning.
Electrolaser centric.
But we don't have a powder bed. Binder jetting, but we are not using binders. We are jetting the material, so it might be a bit similar to material jetting. We are jetting the material, and with the help of the laser, it's melt it and stick to the previous layer or the substrate itself. What about fused filament fabrication? How this one is similar to fused filament fabrication? Think about the wire case, for instance. We said that there may also be wires instead of powders. What happens if they have wire feedstock? So you will have a kind of a nozzle once again, and at one side we will be feeding wires, and at the center we will have a laser. So this is very similar to the fundamentals are similar to fused filament fabrication, especially the wire feedstock case. In the fused filament fabrication, we are feeding filaments. They are kind of wires, and we are heating these filaments at the tip, which is very similar to this process. Again, we are doing the melting operation at the tip of this nozzle, and again, we are following a similar path as we have done in the fused filament fabrication. The paths are similar. And again, if you consider the powder case, the rest is the same. Again, the powders are melted right at the tip of the nozzle. So this is somehow similar to fused filament fabrication systems. And currently, they mostly use 3-axis, but if you remember from the video, I'm sorry guys, I pressed the wrong button. They may also have multi-axis deposition. And especially if you remember the hip joint example, since they have a hemispherical surface and they need to deposit the material always in 90 degrees, that's why they had 5-axis machine, so that they will be depositing the powders always in a perpendicular way. So now this is their joints, and they were depositing the powder in such orientations. For here, for instance, they had such an orientation of the heads. So that's why they need multi-axis heads to have proper surface or uniform surfaces. You can also do it with a 3-axis system, but probably you cannot obtain a uniform thickness around your joints. With the help of this one, they will always have the same amount of material on top of the joint. But if you have 3-axis conventional system, probably you will have extra material here. For instance, the height might be too much around here, but it might be less on the other region. So that's why, depending again on your application, you may prefer to use multi-axis version of deposition systems. Another thing, the advantage, this can be considered an advantage, they have dense products. Why do you think they have denser products compared to other additive manufacturing methods, other metal additive manufacturing methods? How they obtain high density?
Partiküller eriyerek geldiği için aralarında hiç boşluk kalmıyor diye düşünüyorum hocam.
So I couldn't hear you. Can you tell once again?
Partiküller gelirken eriyip ondan sonra birleştiği için aralarında herhangi bir boşluk olmuyor diye düşünüyorum.
Actually, the most important issue here is the speed of the powder. Since we use pressurized gas to jet them, and their kinetic energies are very high, their speeds are high. Once they hit the molten pool, they can actually fill all the gaps, as you mentioned, properly, and we will have almost zero porosity inside the part. That's why we always have denser products with the help of this direct energy deposition systems. And the last one is kind of a disadvantage, but depending again your application, especially implants, high surface toughness values are required, but if it's a kind of a shape to be used in different assemblies, you need to have obviously less surface roughness values, and for that purpose, you need to do further machining. And if it's a complicated shape, if you have formed surfaces, you may not be able to do it easily. You may need to have some 5-axis CNC machines. Otherwise, your 3-axis CNC may not be able to go into some critical regions. It's a nice illustration of the methods. As you see, we start with a substrate. And the examples I have all actually printed on a substrate. This block is called as a substrate, and you cannot actually directly print your part on a bed. Since if you print on a bed, then your bed will be harmed, and you cannot remove the part from your bed, since it's a metal and they are joined with a kind of a welding operation. It's not easy to remove it. You need to have some special equipment to remove from the bed, but if it's a substrate, then you can take it away and remove this part on a different machine. And this is our laser beam, as you see in the schematic. Again, they are using kind of galvanometers to make it faster. And in some systems, you may have such, this is by the way a typo, it's in textbook, this should be powder feed nozzles. We may have a coaxial nozzle system, or we may have such discrete nozzle system. This is a discrete version. We have 2 nozzles, one is on the left, one is on the right. They are depositing powder at very high speeds into this critical region. This can be considered as a molten pool. We have high temperatures here, and once the powders are actually deposited into this region, they will be melted and joined with the previous layer. And this is our layer thickness, and this layer thicknesses are quite higher compared to the other metal additive manufacturing systems. They're not around 100, but they are usually around 200 micrometers. And another thing you can see here is that they have different alternating patterns for each layer to make your part denser and make it stronger. They have, for instance, horizontal infill pattern for the first layer, but actually vertical for the first layer, and then horizontal for the second layer, and vertical for the third layer. This is for increasing the density and the strength of the parts. And we have different trademarks for the same technology. As you see, there are many of them. Laser engine, net shaping, directed light fabrication. This one, direct metal tooling, is the trademark of Instack company we have seen a moment ago. But there are also companies using the same technology, and they name the technology in a different way due to this trademark issues. For instance, laser direct casting, laser cast, laser consolidation, laser freeform fabrication, but they're all using fundamentally the same technology. They are depositing the powder at very high speeds. They have a laser at the center and melting these powders on the part. And they have little differences in terms of the type of laser they are using, the size of the spot of the laser, the power they are using, their power delivery method, whether they have just a single nozzle or a coaxial nozzle, what type of inert gases are they using, do they have any camera for controlling the deposition. So there are many differences, and once they come up with a new difference, they name their methods in a different way. So that's why we have too many trademarks for this technology. Here you see an example, for instance, we have titanium base and then titanium carbide actually layers. This can be considered as a composite structure. We have 4 layers on the titanium substrate. So the main material, the substrate is titanium, but the upcoming layers are titanium carbide. And you can see that their layer thicknesses are not small, more than at least 250 micrometers. This is another picture, and then here we have cobalt, chrome, and other alloys. This is SiFi. The first one, A, is a SiFi. You can clearly see that they have an alternating infill patterns. In this one, I think they are using vertical ones, but in the upcoming layer, they are using horizontal layers. It's quite easy to see in the side view. Another thing is that obviously their melt pool is going into the previous layer. If you remember, this was the same issue we discussed in SLA and SLS systems or SLM systems. If you assume that this is kind of a layer interface, and the other one is here. You see they have kind of melt pools going into the previous layer all the time. They are trying to make sure that we have proper connection between the layers. And the right one is a top view of the same deposition. You can see how the melt pools are follow each other. This is one melt pool, another one. So this is probably going in a kind of a zigzag way. This is how the powders are deposited. Any questions, guys, about the fundamentals of direct energy deposition systems?
Hocam,
Yep.
şu dans kısmını bir tekrar edebilir misin?
Let me draw a schematic here. This is one layer, another layer. So while depositing the powders, as I mentioned, with the help of the laser, we form some molten pools. These are the pools where we have liquid materials. They're called as molten pools, and their size is quite high. They go into the previous layers to make sure that these two layers are joined properly. We have a proper connection between them, and this is done with the help of going into the previous layer by increasing the depth of your molten pool. And we will in a moment see that this is done with the help of adjusting the focus of your laser. If your focus is a bit above the previous layer, then you cannot join the layers together. So these are kind of actually molten pools you can see, and they need to go into the previous layers. Probably we have a kind of an interface at this height. So here you can say that this part is have actually embedded into the previous layer. There's a question on chat. Can we use different materials? Yes, you can use different materials. Even you can mix different materials while you are depositing them. For instance, if you look at this alloy, you have 3 different materials, and you may have 3 different nozzles. Each one will be responsible for different material, and if they are deposited at the proper amounts, you may have the alloy deposited and formed at the part. They are not formed previously, they are formed right on the part itself. So it's a nice way of direct energy deposition. You may even have one layer, let's say cobalt, and then one layer of chrome. This can be done again by having multiple nozzles, and that's a nice property. It gives you high flexibility. So there's another question: can we use arcs? There are also you may have a look at wire arc additive manufacturing. Please, Ayrıca have a look at this additive manufacturing method. We are not going to spend time on this one, but in wire arc additive manufacturing, they are using wires, and also they are using some welding technologies. Some different welding technologies are used to deposit such wires on, once again, substrate or on the previous layers. But the fundamentals are somewhat similar. With the help of these electric arcs, you generate some heat and increase the temperature of these material and melt them right on the specific point. So now let's have a look at some variations among these direct energy deposition processes. The first one is laser-based metal deposition. Is the most commonly used one. For the substrate, we may use a flat plate or an existing part. So this is a nice property we didn't discuss, but that's a very important property of direct energy deposition systems, which means that you can start with an existing part. Assume that you have a kind of a part, a very expensive part, let's say, and it may have a crack at the top surface. Assume that we have a crack here. And once you use this process, you can simply fill these cracks with the powders, melt them, and after the process is over, you can have an actually refurbishing or a rejoining operation, and you can use this part once again. Otherwise, if you don't perform this process, it will be a scrap. But right now, since it's highly costly, you don't need to use it as a scrap. You can do some kind of actually refurbishing or remanufacturing kind of operations and fill these crack gaps with powders and use the same part once again. And on this manufacturing process, we have a deposition hat, obviously, and if you have seen in the previous slides that in the schematics that we have laser optics, we have powder nozzles on the sides, we have gas tubing, inert gas tubing. We didn't discuss it, but in a moment we'll discuss that this process requires an inert atmosphere around the molten pool. And we need to have some filter sensors so that if anything goes wrong, these sensors will simply sense the problem and send some signals to the main controller, and then your main controller will try to fix it on the fly, or if it's not possible, then it will simply stop the process. And in these processes, the kinetic energy of the powders are highly important. They're obviously higher than the effect of gravity. And that's why, with the help of this property, we can deposit the materials in different orientation. It doesn't have to be in the vertical axis. You can have multi-axis deposition. It only depends on the capabilities of your head. If it's rotating, then no problem. You can even extrude, even deposit material in such difficult orientations. And regarding the molten pool, we have quite large molten pools. Their sizes are starting from 0.25 to 1 millimeter in diameter, and their depth might be, as you see, up to 0.5 millimeters. And the thing is that you should be injecting these powders into the molten pool. Otherwise, your powders will not be melted and they will be spread around. Yes, this is a very fundamental thing. You assume that this is the molten pool. So if you deposit powders into this molten pool, they will be melted and joined with the previous layer. But if you deposit powders here around, then they will not be melted and you cannot use these powders. They are all around on your table, and you may try to recycle them, but it's not that easy. So once your electric laser, assume that this is a laser, once this laser moves, then the powders which have been already melted, they will be solidified and joined with the previous layer. So let's have a look at some properties. What happens if you have a small molten pool and rapid traverse speed? So you have a little molten pool and your head is moving at a higher speed, let's say right in this configuration. What happens? Obviously, you have high cooling rate. Since the speed is very high, at the moment at the very instant, the temperature will be very high, let's say 1000 degrees, but once this laser moves away, then the temperature will decrease suddenly, and this will result in obviously high cooling rates. So with the help of it, you can have large thermal gradients, and these will result in different microstructures in your resulting product. So with the help of this parameters, you can determine the type of structures you have, type of grains you have in your final product. Is a nice property. By simply playing with the parameters, you can adjust the type of structures you have in your final product. Yes, and they will be somehow similar to the casted structures, casted grain structures. And this is the same thing we mentioned. You need to have some overlap between the layers, between the let's say scanning lines on the same. Assume that this is a line and this is a layer, and if this is the path to be followed, you need to have some overlap between these regions, and that will result in some higher strength. Any questions, guys?
Hocam bir şey
Yep.
sorabilir miyim?
Sure.
Demin dikkatim dağıldı sanırım da o yüzden tam takip edemedim. Bu powder atıldığı zaman gitmesi gereken yerlerin dışına gittiği de oluyor mu?
Yep, sure.
Tamam. Peki bu o zaman normalde o layer'da daha kalın bir katman olmasına sebep olmuyor mu peki?
No. They are trying to deposit exact amount of powder. So if you have, they are also considering the amount of powders which will be spread around. And they have camera around, so once you see that there is less material, you can increase the amount of material.
Tamam, anladım. Teşekkürler.
You're welcome. And now let's focus on some powder feeding systems, how we are delivering the material on the table. We can use metal and as well as some ceramic powders. We will have, we need to use actually powder more than the volume of the material. Obviously, we need to have some recycling, and as your friends asked, you always have powders on the table, and I think it was also clear in the video. We need to recycle them with some different equipment. So this is quite difficult to recycle since we don't have a proper bed. It's not stored in a bed. All the powders are around. You need to have special equipment to recycle them. And again, very similar to selective laser sintering or melting, we have a critical energy value. If the density of your energy is less than this value, obviously you will not be able to form the molten pool. If that's the case, then any powder will not be melted and you cannot continue with the manufacturing operation. So the height and the volume of this deposition is quite important. And the molten pool, the size of this molten pool, seeing that again we will be assuming that we're kind of an elliptical shape for the molten pool, and the height and the overall volume of this molten pool is quite important, and they depend on many parameters like the focus of the laser, the scan rate, the laser power, the amount of powder you are depositing on the layer, the surface quality, surface morphology of your substrate or the previous layer. And we should be careful about these and try to have a proper manufacturing. This is a schematic of the laser. As you see, we have some optics here at the center. This is our laser beam, and the green region is actually the critical beam energy. This is in this region, the energy is above EC, which means that we can form the molten pool around here. And this is the spot size at the focal plane. This is the focal plane of our laser, and probably you'll have a molten pool around here. Usually that focal plane will be around the center, not exactly, but that will be around the center. So we have some terms. For instance, they name this part, this region, as buried spot region, and the below is exposed spot region. And after that green part, we don't have the critical energy levels, so we cannot melt any powders or any layers underneath. So in summary, to have a proper molten pool, you need to adjust all these parameters carefully. Otherwise, at some point, you will need to stop this deposition process. I think it's better we stop now. Any questions, guys? There's a question on chat. Do we have shrinkage? Yes, since we are melting the powders and we are doing the joining operation at very high temperatures, you'll have shrinkage, but since we are always continuing depositing the material, it will not affect the overall shape of the part. You have shrinkage, but it's not affecting the overall part. Since you are always monitoring this operation with the help of cameras, and they will be checking also the size of your part. If it's less than desired values, it will deposit more material and try to satisfy your dimensional requirements.